Hello, welcome back to Data-Driven Nonlinear Dynamics and Vibrations. In this video, we are going to continue and finish Chapter 6, which is on maps. And in this section, we are going to cover Poincare maps. So a Poincare map is a discrete time system or map that is associated with a vector field. Effectively, we create Poincare maps from continuous vector fields, and it's a way to reduce the dynamics down into a simpler form that we can then interpret and analyze and try to understand the behavior. So the basic idea is to consider the flows of the vector field. And if you recall, the flows are in a sense, the motion of the phase space in whatever higher dimension that might be. And then you consider those flows and then construct some kind of surface that the flows will always intersect, and then study the dynamics on that surface rather than trying to consider the entire flow. We just consider what's going on that particular surface. And then if we change that surface, then we can also study what happens under different conditions. So for example, if we consider a three-dimensional vector field with phase variables x1, x2, and x3, we could then define some surface S at a height of x3 equals h, and then we could study the points that intersect that surface as shown here in this figure right now. So here gamma, capital gamma that I'm circling, that is the flow in this three-dimensional phase space. And our surface S that I just circled is shown there. It's at some height h, and what we're looking for is how the flow intersects that curve, or how the flow intersects that surface. And the key thing here is that we only want the flow to intersect, we only want to consider points from the flow that intersect in a particular direction. So you can see that here we consider P0 when gamma is moving down, and then it comes up through and it intersects the surface a second time. However, we skip that point because we're only considering when x3, the velocity is negative, and so forth for P2. So like I said, the points of intersection correspond to the cases where x3 dot is less than 0, so it's negative on the flow gamma. You could choose to do the opposite. You could look at what happens when x dot 3 is greater than 0. The height h here of the plane S has been chosen such that gamma will continuously cross that plane. If we chose h to be sufficiently large, we could create a plane that the flow never intersects, or potentially a flow only intersects once or twice, depending on the dynamics of the system. So the proper choice of h, or the proper positioning of this surface, is really important. So then the points P0, P1, P2, and P3, and so on, those form this 2D Poincare section, or the 2D Poincare map. And the Poincare section itself is a continuous mapping, let's say some function g, of the plane S into itself, such that we have a point P k plus 1, and then this is equal to g applied to pk, which is equal to g applied to pk minus 1, or following our notation for maps, we can write this as g squared applied to pk minus 1, and then we could extend this expansion all the way down to p0, or the initial condition, the very first condition of our map. So the nice thing about Poincare sections and Poincare maps is that they reduce the continuous flow of some vector field to a discrete time mapping. The downside is that the time interval between each point is not necessarily constant, and you may not necessarily know what that actually looks like as well. So before we go on and kind of analyze Poincare maps, let's just go over why should we care about Poincare maps. And the answer is first that they reduce the dimension of the problem by eliminating at least one of the dependent variables. And second, they allow us to study the global dynamics of lower dimensional vector fields with phase spaces of dimensions less than or equal to 4. So particularly, we can reduce the dimensions down for let's say a system with 4 phase variables. That would be the equivalent of a 2 degree of freedom vibrating mechanical system. we can reduce the four-dimensional phase space down into a two-dimensional plane that is very similar to a phase portrait in the sense of what periodic orbits do. You can also do this with three-dimensional, systems of phase variables dimension 3, for example, a harmonic oscillator that is forced, or a nonlinear Duffing oscillator that is harmonically forced, where you introduce theta and use theta instead of time. We can use Poincare maps to reduce down the dynamics of those systems. So for those kinds of systems, the Poincare maps allow us to really understand what's going on and interpret the behavior of this. Now for real complicated real structures, for example, you could consider doing a reduction down or some type of modal expansion and truncation so that you only have two modes and therefore have a resulting four-dimensional phase space. You could then apply Poincare sections to the underlying modes based on that expansion, whether you've done a Galerkin projection or maybe some type of proper orthogonal decomposition, or you've just done a simple modal decomposition and just used assumed mode shapes and incorporated that and included coupling that way. All right, so we're going to talk a bit about what Poincare maps look like and their behavior for particular points and particular types of flows or particular types of orbits. In this discussion, we're going to use the word flow and orbit to really kind of mean the same thing. And so first we want to start off if the flow is periodic, then the flow is going to return to the same point after a single period. It's going to just circle back, and the flow may not necessarily be a circle, but every time the orbit or flow comes back to intersect the Poincare section, it's going to intersect at exactly the same point. And it's going to do this for all time. So as a result, periodic orbits are going to appear as fixed points on the Poincare map. If the periodic motion associated with a fixed point on the Poincare map is stable, then the fixed point will be enclosed by concentric closed curves. And as a result, stable periodic orbits become centers on the Poincare map. And so you can see in the diagram here, in the dashed black line, we have our periodic orbit intersecting at P0, and then some type of orbit that is close to that periodic orbit. And if you recall, in this sense, a periodic orbit is a periodic solution, which corresponds typically in terms of nonlinear vibrating structures. This is what we would consider to be a nonlinear normal mode, for example. As you recall from chapter 5, we defined nonlinear normal modes to be periodic solutions, not necessarily synchronous, but periodic solutions to the response. Consisting of a single frequency typically as well. So when you're close to a periodic orbit, but not necessarily exactly on that periodic orbit, which means you're not exactly on a single NNM branch, you get a multi-frequency signal, and as a result, you end up with multiple points surrounding this fixed point. Now, if it's stable, they will orbit around it for all time, and that's why we get these centers. Similarly, a unstable periodic orbit ends up becoming a saddle point on the Poincare map. And that's because if it's unstable, orbits will tend to move away from it, leading towards this type of saddle node behavior that we've seen in the phase portrait before. So similarly, period K orbits will pierce the Poincare section K times before closing. And so thus period K orbits appear as K fixed points. And in the diagram here, I've shown there is a period 2 orbit, and you can see how along this orbit the intersections with the Poincare map will oscillate between P1 and P2 to P1 to P2 and so forth. So period K orbits arise in the flows with multiple frequencies that are commensurate. This is when you have internal resonances typically. If we're thinking nonlinear vibrating structures, this is evidence of an internal resonance being present in the response. And you'll end up with, for example, a 3-to-1 internal resonance, you'll end up with 3 fixed points. For a 2-to-1, you end up with 2, and so forth. All right, so then quasi-periodic orbits. These correspond to flows with multiple frequencies that are incommensurate, meaning that they're irrationally related. And in this case, when you have, for example, when you have two frequencies that are incommensurate, the orbit ends up existing and wrapping around some kind of torus, which, if you're not familiar, is just a donut shape. So the flow, or the orbit, as for example shown in this diagram, will wrap continuously around that torus, meaning that every time it comes to the Poincare section, it will intersect at a slightly different location. And in infinite time, this quasi-periodic orbit will densely fill the torus. That means it will touch every single possible point on the torus, and as a result, we will end up with a closed curve in the Poincare map. Now here, I've drawn this torus to just be a perfect donut, or a cylinder that wraps around on itself, and as a result, the closed orbit ends up being a perfect circle. That is not necessarily going to happen in real systems. This is just an illustration of this behavior. And then, as I said, with infinite time, the orbits will densely traverse the torus and touch every single possible point. And then lastly, you can get things like aperiodic orbits, which are typically associated with chaos being generated, and meaning there are no periodic orbits. There's just periodicity in the response. And these will typically appear as point clouds. However, you can sometimes get some very interesting structures that appear in that chaos, which we will typically refer to as chaotic attractors. And it will depend on the system that you're studying as well, what exactly these structures look like and how they change. We'll see one in the second example that we'll talk about in this video. All right, so let's now talk about how to compute Poincare maps. And in general, there exists no general analytical method to compute Poincare maps for arbitrary vector fields. But there are three cases where you can construct these systematically or analytically in a way that you don't need to do any kind of numerical calculation. The first case is when we are near to a periodic orbit. Since you can compute the stability of the periodic orbit, you can then compute and construct what will happen around that orbit. The second is near what's known as a homoclinic orbit. And just to explain what this is, a homoclinic orbit is where you have a single fixed point and the orbit leaves and then wraps around and intersects back to that. So when you have homoclinic orbits, you can construct a Poincare map systematically. We're not going to go into too much detail on how to do this systematically. And the third is when you have time periodic ODEs. For example, a linear harmonic oscillator is subjected to a harmonic excitation. However, like I said, there's no general analytical method for applying these to just any arbitrary vector field, and as a result, you'll typically compute Poincare maps numerically, and we're going to discuss how to compute these for a Hamiltonian, which means no forcing, no damping, meaning that its energy is conserved. Hamiltonian 2 degree of freedom system, or 2DOF system. And then second, for a harmonically forced systems. So for the harmonically forced example, we will look at just a Duffing oscillator, but you can still apply the same technique and idea to multi-degree of freedom systems. And at the end of the video, I'll pull up a research paper that a student and I wrote where we applied this Poincare section idea to try and study the behavior of a 2 degree freedom system harmonically excited. So for our 2 degree freedom system, we've drawn the schematics shown here. We have 2 degrees of freedom, X and Y. The first oscillator we call the linear oscillator. The reason is that it is grounded linearly with just a linear spring there. The second oscillator we call the nonlinear oscillator because it's non-linearly attached or installed onto the linear oscillator. So the background for this system is that we were studying how energy flows through mechanical structures and using a simple 2-degree freedom system to investigate that kind of behavior. And in that kind of context, you tend to think about some linear primary structure that you install a nonlinear component on. And in our case, we chose to make our component have equal mass to the linear primary system. And this is where we get this nomenclature, linear oscillator, nonlinear oscillator. In terms of this class, it's not really relevant, except that when you go to look at the Poincaré maps in the notes, you will find that they are labeled LO, NO, and this is where this nomenclature comes from. All right, so the equations of motion for this system are the following. We'll have x double dot, let me draw a better x double dot plus x plus the quantity x minus y cubed, x minus y cubed. This is equal to 0, that's equation 17, and then we'll have y double dot plus quantity y minus x cubed, that is equal to 0. So our first step here is that we're going to arrange this into a first order ODE or into a autonomous phase space system or state space system. To that end, we're going to say that z1 is equal to x, z2 is equal to y, z3 is equal to x dot, z4 is equal to y dot. From there, we will get the following, that z1 dot is equal to z3, z2 dot is equal to z4, z3 dot, this is our equation of motion for x, it's going to be equal to minus z1 minus the quantity z1 minus z2 quantity cubed, and then z4 dot, this is going to be equal to minus the quantity z2 minus z1, that quantity cubed. So we now put this into our state space formulation, which is how we would simulate this numerically anyway, so this is now useful here. If we had any forcing, we would have to introduce an additional term to convert it into an autonomous form. Here we did not have any external forcing, so we do not need to convert to into an autonomous form. And then we can then just write this simply as z dot is equal to some function f of z, where z here lives in R4. So z is our phase space vector, which contains all of the phase space variables or state space variables, and it's dimension 4. What we're now going to do is compute the Hamiltonian for this system, or the mechanical energy, because it's just a vibrating structure, mechanical structure, and then we're going to set that equal to a constant. And once we set it equal to a constant, we now have an additional variable h that we can use to reduce and eliminate one of these phase variables. So we currently have 4 phase variables, and what we want to do is introduce a 5th variable, which will be the energy level. And once we define what the energy level is, because the energy is conserved in this system, we can then use that energy to determine one of the phase variables, and we're going to choose one of the 2 displacements. And as a result, because we can just arbitrarily choose what the energy level is, we can then study what the behavior of this system is under different energy levels as a result. So let's go through this first. So we're going to first compute the Hamiltonian, and we're going to say that our Hamiltonian h, big H of the vector z, of z here. Now h is a Hamiltonian, or in this case it's going to end up being conservation of mechanical energy, or just simply the mechanical energy. This is equal to 1/2 z3 squared plus 1/2 z4 squared plus 1/2 z1 squared plus 1/4 times z1 minus z2 to the 4th, and then we're going to set that equal to a constant h. Now we can also write this big H here as a function of x, y, x dot, and y dot. And then this will be equal to 1/2 x dot squared, that's our kinetic energy for the linear oscillator, plus 1/2 y dot squared, that is our kinetic energy for the nonlinear oscillator, plus 1/2 x squared, that's the potential energy for the grounding linear spring, plus 1/4 times x minus y to the 4th, and that is the potential energy for the coupling spring, and then this is equal to h, lowercase h. So again, h is some constant that we get to choose, and as a result, we can then use it and this Hamiltonian, or this mechanical energy, we can use this equation to eliminate one of the variables. So, for example, if we want to go with and try and understand the phase space of the linear oscillator, what we need to do is pick a value for h and then say use this mechanical energy to solve for the displacement of the NO. So y here is equal to h inverse of x comma x dot comma y dot, and we also need h in here. So h is a constant. We then need to prescribe what x dot, and y dot are, at least for initial conditions, and then we can compute an initial y value as well. Furthermore, for any x dot, y dot, and x in the flow, for this particular energy level, we can always compute what y is if we know those three and we know what the energy level is. So in terms of computing the Poincare section, we will need to specify the initial conditions x0, x dot 0, and y dot 0 in terms of doing a numerical computation. We specify what each of these are, we know what h is, and then we can compute what y of 0 is, and then we can do our numerical simulation. And then we'll explain how we then construct the Poincare map in a moment. If we wanted to do this for the NO, we will instead define, give me 1 second, I need to move these to layer 2. And let me lock layer 2. Alright, so if we're going to do this for the NO, what we need to do is define x as being equal to h inverse of y, comma x dot, comma y dot, comma h. And here we need to specify, and I left out the word specify above, so let me go ahead and add that. We must specify these three. And in this case, we must specify or choose y of 0, x dot of 0, and y dot of 0. Now here we've chosen to eliminate one of the displacements. However, you could, if you wanted, choose to eliminate one of the other phase variables or one of the velocities. However, for your homework, you should just choose one of the displacements and eliminate one of the displacements. So from here, we're going to then, after selecting our initial conditions, we are going to then integrate numerically for different sets of initial conditions. And then we're going to find, in the case 1, we're going to find the values of x and x dot when, or at times when y is equal to 0 and y dot is greater than 0. Now you could also choose y dot less than 0. In the Poincare maps that I'm going to show, we have chosen y dot to be greater than 0. This is so that we only intersect in a single direction. And then for case 2, we need to find, let me just add real quick here, we need to find values of So here we need to find values of y and y dot when x is equal to 0 and when x dot is greater than 0. So in your notes, you'll get a couple of different pictures of Poincare maps. On the left is the case 1, where we have set y equal to 0, meaning that we've set the displacement of the NO to 0, and we're now looking at the values of x dot and x. On the right, we have the opposite, where we've set x equal to 0, and we're now looking at the values for y and y dot. So left side, we have the Poincare map for the yellow. On the right side, we have the Poincare map for the NO. Now, I've included here some of these for different dimensions, for example, or for different energy levels. And we'll briefly just talk about these, and then I'm going to switch to a video where we computed a ton of these, and we'll talk a bit more about what can emerge from these. So for example, in the first two that you see here, we actually only have a single fixed point. I'm going to draw with the laser here. Our first fixed point is just in the center for both of these, and that is because at very low energy, while there are still two nonlinear normal modes, they are localized in each mass, which means that in this case, the first nonlinear normal mode only has motion in the NO, while the second NM only has motion in the LO. And as a result, there's only a single fixed point in each of these responses. If we now move up an energy level, we can now see that on the LO on the left plot, there is at least a single fixed point in the center, and that one is stable. And then beneath it and above it, there are actually now two fixed points that are now unstable. For the NO on the right, you can see that there's a single fixed point, at least a single fixed point in the center. There could be other fixed points surrounding it. Then there are 5 fixed points around it that I've just circled that are stable. This represents a 5-to-1 internal resonance between the NO and the LO. You can also see that it's accompanied by 1, 2, 3, 4, 5 unstable fixed points, and this represents the unstable fixed points that are associated with that 5-to-1 internal resonance. There's also other unstable fixed points up here that I'm now circling, and there's another one down here. And potentially, although we can't see it here, there might be some stable fixed points where I've just circled on the screen. And one thing to note is that the boundary of these Poincare maps represents the maximum, the entire energy. So at the boundary, all of the energy is still in one of these two masses. Okay. If we go up again in energy level, looking at the left plot here, you can see that the LO has a single fixed point here, and then it has some quasi-periodic orbits that I've just circled on the top and the bottom. And otherwise, it's just surrounded by some nice fixed orbits with some emergence of some chaos at the boundaries that I'm now highlighting, shown here. On the right, if we look at the Poincare map, you actually end up with a single fixed point in the center, and then you have 3 fixed points near the boundary here, and these represent a 3-to-1 internal resonance between the 2 degrees of freedom, or the 2 NNMs in the system. If we go back up higher in energy, we now see that there's suddenly, on the left plot, there's now an emergence of 2 fixed points, one that I'm just circling right now, and then another one up here. And this is actually where the 2 NNMs begin to cross each other, and there's some intersection and conversion and so forth. If you take a look at the right plot, you can see that there's a single fixed NNM in the center, and it is potentially surrounded by some unstable fixed points. And then we also have a fixed point here, fixed point here, and a fixed point here. These represent a 3-to-1 internal resonance. And then there's another, let me just let the laser go. Here's another fixed point, and another fixed point is over here. And these also represent a 3-to-1 internal resonance. If we go up to higher energy here, you can start to see even more fixed points start to emerge. and they begin to become surrounded by seas of chaos. So just looking at the LO shown here, there's 6 different fixed points, and there's more fixed points up here. And then everywhere around it where you don't see any kind of structure, well, there's some quasi-periodic orbits down here, but these areas that I'm highlighting now, these are all just chaotic regimes, where you just have a sea of chaos surrounding these fixed points. And if you look at this, the one for the NO, you can see that there's a really nice, interesting structure going on here. You have points where you have a single fixed point, another fixed point here, and these are surrounded by 3, even maybe 4, 5, 6, 7, many fixed points actually. There are many different fixed points that arise here. This is due to the bifurcations in the dynamic leading to different types of internal resonances that occur, different types of nonlinear modes that appear due to bifurcations in them, and so on forth. And then they're all surrounded by these chaotic regimes, such as the ones shown here. All right, if you take a look at one more energy level, this is the highest energy level that we computed here. Beyond this, you start to get a lot of chaos and less structure emerging in the response. For the LO, you can see that there is at least a fixed point here, one here, and maybe some more fixed points around here. It's hard to tell. And then everywhere else, we just get this chaos emerging with maybe some strong chaos or some kind of attractor emerging there as well. And now looking at the NO, you get nice structure around here, and then some here and here, here and here. This looks like a 7-to-1 internal resonance, although it may not necessarily be fully periodic. And some more interesting stuff going here, with the rest of this being purely chaotic. Okay, so with this, I'm now going to switch and show a video of the evolution of this Poincare map. And I'll try and pause the video and go through different points of it, and then we will then move on and look at our second example. Okay, I know I said that I was going to show the videos for the LO and NO Poincare maps. However, they ended up being longer than I wanted, and so they're actually going to be at the end of this video so that we can instead now go through the second example. So one thing I did want to add is that the codes is provided for these Poincare maps, shown here. In this, we are using an initial velocity, such as the one shown here. We're using these different initial velocities to compute the energy levels that we use to construct the Poincare map. So we take some initial velocity, we then compute the equivalent kinetic energy shown here, and then we use this rhos as a way to construct the energy levels for the Poincare maps. In your homework, you're going to want to just define what rho is, define what this energy is, and then go directly from there rather than using this initial velocity. So with that, we're now going to move on and take a look at our second example, which is that of a forced stuffing oscillator. Now, this approach can be applied to other systems, and I'll show some results at the end of the video after those LO and NO Poincare maps. I'll show some examples where we applied this to a 2-degree freedom system to compute Poincare sections for a harmonically forced system. However, now we're just going to focus on this Duffing oscillator as shown here. The Duffing oscillator has a linear stiffness, a negative linear grounding stiffness, a positive nonlinear stiffness, a damping coefficient of 0.25, and then a mass of 1. And it is excited with some force F times cosine. That F could be varied, although we'll only look at a single value in here. However, you can then change the value of F and look at how the Poincare maps evolve. So the equation of motion governing this system is x double dot plus 0.25 times x dot minus x plus x cubed, and then that is equal to F times the cosine of omega t. And you can change omega and choose what that you want. We'll look at just a single value here when I think omega is equal to 1. We'll see when we get to the codes. The first step we're going to do is we're going to arrange this into an autonomous form. We're going to start by converting to state space. To do that, we'll say x1 is equal to x, x2 is equal to x dot, and then from this, what we'll end up with is x1 dot is equal to x2, x2 dot is then equal to x1 minus x1 cubed minus 0.25 x dot that should be x2 plus f times the cosine of omega t. From here, we're going to convert to autonomous form, and that will include phase variables of, well, x1 dot is equal to x1 or x2 dot is equal to x1 minus x1 cubed minus 0.25 x2 plus f times the cosine of theta. And theta is now a new phase variable that we've introduced in order to put this into autonomous form. And then theta dot is now equal to omega. And so here we now have an autonomous form. You could say something like z dot is equal to f of z. And then it lives in the domain x1, x2, and theta, living in the domain of R2 with S1 for theta. So then the flow, if you wanted to describe the flow, we could say that phi of t comma x1, x2, theta, this is equal to, x1 of t, x2 of t, theta of t, which is then equal to omega t plus some theta 0. And this lives in mod 2 pi, meaning that theta goes from 0 to 2 pi and then reflects back. From here, we're going to now define our global Poincare sections, and then we're going to just do a quick sketch of what this would look like for an example. So let's say theta is equal to pi over 2, 3 pi over 4, pi, and 3 pi over 2. We're going to look at those sections. All right, so what are we actually going to be doing? Let's draw our phase space. And do a little bit better than that. So down here, we're going to have x dot and x, and then in the vertical axis, we will have theta, and we're going to have a value of 2 pi here, well, 0 down here. We have some plane where this flow lives in. We have another plane up here at 2 pi, like follows. And so for some, let me see if I can redraw my plane up here to make it match. Oops. Alright, so we got some plane here at 2 pi, and what we want to do is construct another plane, say at pi over 2, and then so our flow will start at some initial condition here. It will come up, reach another initial point here. Flow is going up. Goes down here, comes back up to a point here. See, the flow is going up, and then it will come back down here, come up and hit up here, going back up. And we can now see that the flow has intersected the plane pi over 2 as shown here, and then we'll get P0, P1, P2, and this is how we're going to construct our Poincare map, is using this plane at pi over 2, looking at what the values of x dot and x are in this case. After transients have died out, at least, if you have damping. If you don't have damping, then transients will never die out, so you don't have to worry about that. If you have damping, then looking at where it intersects after the transients have died out, and then we'll plot what this looks like over many cycles. And we're going to do that in this case for theta equals pi over 2, 3 pi over 4, pi, and 3 pi over 2. From here, we're then going to numerically integrate and then find the values of x1, x2 when the flow intersects those Poincare sections. That's again when theta is equal to pi over 2, 3 pi over 4, and so on. And like I said, if damping is included, you should only find x1 and x2 after the initial transient response has died out. And so here are the Poincare maps that appear for pi over 2, 3 pi over 4, here's pi and pi over 2. And in this case, although it is chaotic and aperiodic, there are these strange attractors, or these attractors we call them strange attractors, that appear in the response. And these end up becoming consistent, and if we simulate this for a long enough time, we'll find that all of the points end up lying on these attractors, and they stay there for all time. They're not necessarily periodic, and they may not necessarily follow the orbit in a periodic nice loop. They may jump around this orbit, but they all end up being on these attractors. And then lastly, you can find the code I used to compute this here. You can use this code and modify it for your homework. Alright, so here is the Poincare map for the linear oscillator. We've computed this for many, many energy levels. E here is our equivalent H. And the way we've done this is that we first postulated that there is some initial velocity in only the LO or only the NO, and all other initial variables are 0. We then compute the kinetic energy for that equivalent, for that initial velocity, and then we use that kinetic energy as our energy level for the Poincare map. And that's what you'll see when we have a V0 up here and an E as well. So here we're at a very low initial velocity, very low energy, and lower than what was included in the notes. And you can still see we get these nice periodic orbits as shown here. I'm just gonna click play, and then I'm gonna cycle through this manually because there is a lot of detail here. You can see that, for example, here is kind of the emergence of another fixed point, but we didn't have enough energy, or we didn't have enough resolution or energy to capture that, so we actually end up skipping that. We'll keep going, and eventually we'll start to see here we actually see the emergence of another set of fixed points. So we have if we go back, you have the original fixed point right here. It moves up, and then actually what emerges here, this is actually the emergence of 2 fixed points, one unstable and one stable fixed point. That's why you get this kind of horseshoe shape as shown here. If we go to the next energy level, which is just slightly increased, you can see it's an increase of 0.001 in terms of that initial velocity, a small increase in energy. And suddenly we now have 2 stable fixed points, one up here, one down here, and then an unstable fixed point. Those will stay for a while, and then we'll keep going until suddenly what will emerge is a 3-to-1 internal resonance that we'll eventually get out of this. Actually here there's a fixed point, 2 unstable fixed points. If we keep going, we'll eventually start to see some internal resonances. Here is suddenly the emergence of these 3-to-1 internal resonances. You can see we actually have a fixed point here. We have 3 fixed points surrounding it. Now the orbits are not closed here because they're all quasi-periodic, and we did not integrate to enough time for them to close. But if we integrated up through infinite time, we would 100% close and touch every single point, and we would get a fully closed curve at all positions. It would be continuously closed. If we go up, you can see now that we have these now 3-to-1 internal resonances, and you can now start to see that they're much more periodic with these orbits, and we do get these closed orbits here. Keep going. We'll see some more interesting stuff up here. Here is actually the emergence of like a 4-to-1 internal resonance. It actually switches between a 4-to-1. You can see there's a 2 fixed points. So this is a 2-to-1. Here is back to these 4, and so forth. Here is still a 4, back to 2, 4, 2, and so forth. Here we're getting these quasi-periodic responses. Again, we're not computing enough. Some interesting stuff has been happening up here. There's actually kind of the emergence of maybe a 3-to-1 over here, or maybe just some quasi-periodic orbits. Here you get this kind of dense region where you just get a chaotic response, and then suddenly there's an emergence of a second fixed point, and looks like there might be an unstable one up top there as well. Yep, and indeed we can see that there's now this emergence of a stable fixed point and an unstable fixed point. And then there's some other points around here. If we keep going, we now have these two modes as shown here. So this is our first NM, second NM, or maybe the top one's the first, the bottom is the second. You can always check for those things based on the responses. Let's see. We're going to keep going through this. You see now, in this energy we now have, these two fixed points that now exist and persist, actually. And what is now happening is the bottom fixed point, this is actually probably a regime we're starting to do some type of mode conversion, perhaps, where this bottom fixed point will actually try to exit the response. You can see now have an unstable fixed point there as well. Or we might end up with the emergence of some type of resonance condition. And indeed here you can see that we do get this saddle node bifurcation. In fact, here you can get this homoclinic orbit as well, where it starts from one fixed point and then it goes around the orbit and comes back to itself. And then you get these kind of horseshoe shapes. And what we're looking at here is now the merger of these two fixed points, and now they're gone. And looks like there might be a 3-to-1 going along here as well. Many more things. Here you get a lot of different fixed points, a lot of different kinds of interesting interactions that are occurring between the two masses and NMs. You can see we have unstable fixed points shown here, corresponding to some unstable types of behavior, emergence of new fixed points, or the destruction. Is hard to tell with this quality. Looks like a destruction. And we found that around 0.37 there was a very interesting 3-to-1 internal resonance that popped up and consistently happened. You can see that is indeed shown here. There's also the emergence of a 5-to-1, again being another odd order. Again, this is a harmonic system, so a lot of these types of internal resonances may not appear in a damp system. We're just going to keep going. In fact, interestingly, around this upper branch, you can see there are now an emergence of, again, a 3-to-1 shown there. You can see now we're getting these regions of just pure chaos where there's no or aperiodic response. Let's just keep going. Yep, here we're getting these islands of maybe a fixed point surrounded by a sea of chaos is what we would say. Again, we're still maintaining this 3-to-1 resonance and the 5-to-1 as well. If we keep going, you can see that we still have this 5-to-1, but surrounded by a sea of chaos. And the 3-to-1 emerges and stays there. And we've now somewhat lost that 5-to-1. Let's keep going on up. And you can see there's a whole emergence of some really interesting behavior. Down here we have a couple different fixed points and solutions around them. In fact, there's one fixed point and there's actually surrounded by 3 fixed points. And then there's some kind of orbits around here. In this region and surrounding it, you just get pure chaos. And then up here we have these other fixed orbits. Let's actually scroll a little bit faster through this. Go towards the end. You can see that what were fixed orbits up there have now given way just to pure chaos, although there's still that 3-to-1 fixed orbit. But at the bottom we have this single periodic or fixed point, and otherwise everything is just becoming chaotic. And if we go all the way up to the highest energy level that we computed here, which is E equals 0.5, what you end up finding is that there's just a sea of chaos up here with maybe a few islands of stable fixed points. There's some type of unstable, semi-unstable, something going on here, and then you have a single stable fixed point down here, and that represents the nonlinear normal mode at very high energies. This here is the Poincare map for the NO. Starts off with just a single fixed point in the center here. We're gonna go frame by frame through this. and you can see those orbits are getting tighter and tighter and tighter. There's suddenly now an emergence of what looks like a 7-to-1 internal resonance. Again, damping will tend to kill this type of behavior. Here again, there's a 7-to-1 internal resonance. We should start to see also the emergence of a 5-to-1. In this case, we have the 5-to-1 up here. You have these 3 fixed points on top and the 5 on the bottom here. Still, you have a 7-to-1 in the center, followed with these 5-to-1 inside here. That 7-to-1 is kind of there, and it will eventually kind of disappear as the 5-to-1 takes over. And from the outsides, we now actually have the emergence of what looks like potentially a 3-to-1, but we'll have to see as this grows. In fact, we now have here 3 unstable fixed points. You can see that with the 5-to-1, we have the interior 5 stable fixed points and 5 unstable fixed points. And so on the outside, we have 3 unstable fixed points here. There's also another unstable fixed point down there. We just let this keep going and see what emerges out of this. And indeed, you can see that there's a stable fixed point here, stable fixed point here. These unstable fixed points have not actually entered, and it looks like there's 1, 2, 3, 4, 5, 6, 7. There's actually 7 here that have entered in, and that 5-to-1 is still in the center there. Now we have the emergence of these 2 fixed points starting to enter in here. There's now another fixed point down here. If we keep going, so now again we have this 3-to-1 at the top here, this kind of 5-to-1 in the center, and then suddenly we get here the emergence of, this looks like 1, 2, 3, 4, 5, 6, 7, to 7-to-1 again, another 7-to-1 with potentially a 3-to-1 on the outside, a 5-to-1 on the inside. So we get all kinds of interesting and crazy resonances that arise in this response at this energy level. Let's just keep on going here. Those 3-to-1s have now seemed to have morphed into 5-to-1. Let's actually just back up a bit. So here we have 3-to-1 internal resonance. We have some other things going on here. These are probably very high order internal resonances that would not show up in a real response. Yep, this looks like a typical 3-to-1 where you've got 3 different fixed points, and then you've got this kind of triangular shape in the center. And then we're going to suddenly get the emergence of another mode here, and maybe some more fixed points down here. Here's this, again, another type of 3-to-1 that can occur. We have these 3 unstable fixed points, 3 on the outside, and so forth. Let's keep going, and yep. And now we start to see chaos emerging in between these different fixed points, or aperiodic responses, and you can get some really interesting geometric shapes surrounding the single stable center fixed point. And all of that chaos that we had inside here, if we go back to like here, all of this chaos, and you see this nice triangle, all of that chaos is going to give way to closed curves indicating, you know, stable periodic, or not stable periodic orbits, but this has now become more regular and maybe quasi-periodic, or just periodic in general. It can rise to all these different curves, and they all start to come in and merge into a single stable fixed point in the center. We now actually have another stable fixed point at the top there, a whole bunch of interesting stuff going on here. You can see there's all kinds of different types of resonances occurring, different types of saddle node bifurcations showing up here. If we keep going up, we start to get chaos, or aperiodic responses, I should say, surrounded, you know, these areas of stable fixed points surrounded by a sea of chaos. There's really interesting stuff going on in this central point, and then you have, you know, another fixed point up here, plus surrounded by three fixed points. We'll just keep going through this. Here we've actually lost a lot of the external structure, and we've now just got chaotic or aperiodic regimes in the outside. In the inside here, it looks like we have, well, here we have a 7-to-1 internal resonance. We've got the 3-to-1 internal resonance there. And let's just see what happens as we go up. A lot of chaotic, a lot of aperiodic regimes. We had in the center here, we end up with we have single fixed point, and then the 2-to-1 here. Looks like we end up with a 4-to-1. Around here is something like a 9-to-1, maybe a 10-to-1. Actually, it looks like an 11-to-1 actually. So you can get all kinds of crazy high dimensional internal resonances, which damping would tend to kill out. All right, we're gonna scroll on ahead to save some time here. And so at very high energy levels, we end up with a single stable fixed point around here, a sea of chaos up here. There is a stable fixed point right over here, and some surrounding it as well. This is a paper where we computed Poincare sections for a harmonically forced 2-degree of freedom system. You can see the title up here. I'm just going to briefly show you the structure that we considered. It is a 2-degree of freedom oscillator, and in this case, it is exactly identical to the parameters used for the first example in the notes, except that we have now incorporated damping. Here are actually what the two nonlinear normal modes look for the system. The bottom black one here is the first, the S11 plus branch. Above that is the S22 branch. And then you have some subharmonics showing 3-to-1 and 5-to-1 internal resonances. In this case, we're actually trying to understand energy, so we kind of define a way to investigate and interpret energy behavior. From there, we can effectively compute what we call normalized maximum kinetic energies. We go from there, we can plot receptance plots as a function of forcing frequency, forcing amplitude. So in this case, you can see that we considered a force applied to the LO. We also considered a force applied to the NO as well. I believe this first section is where we consider the response when the LO is excited. You can see some points here. Here are some plots that we called the NMKEs, the normalized maximum kinetic energies. We sampled a few different points from here, and this is where we computed these Poincare sections. I can give you the paper, it's included on Canvas as well, but I wanted to just go through and take a look at some of these points shown here. So for example, for the very first point, we just have a single periodic response, just a fixed orbit shown here. One thing I should also explain is that we're applying zero initial conditions, we're then simulating response for a time of 20,000, and then applying a small disturbance, and then continuing to simulate for another 20,000. We're then sampling what's going on in the last time of like 1,000 or so, I think it's last 10%, it might be last 1%. And we're doing that both before and after the disturbance at the end of those. So you can see here in point 2, before the disturbance, we have a nice single fixed point for each of these, and it's nice. It's actually, a single harmonic response here. Then after that disturbance, we suddenly get a closed loop indicating a quasi-periodic response. Here you can see these kinetic energies as well. If we go to another point here, we actually have a 3-to-1 internal resonance shown by these 3 fixed points. After the disturbance, we also have these 3 fixed points. If you zoom in on this black curve right here, black is for the LO, cyan is for the NO. If you zoom in, you'll find that there's actually 2 fixed points here. Here's a case where we have a 2-to-1 internal resonance, and it's preserved after that impact, or that disturbance force. Here's a case where we have a closed loop indicating that we have quasi-periodic responses. In this case, before the disturbance, after the disturbance, we just have a single fixed point, same thing, single fixed points here. Here's a case where we have nice single fixed points. Actually, this is a 2-to-1 internal resonance, so 2 fixed points, and then after that, we just get chaos, or aperiodic response, actually, where the response is just aperiodic, and you just get these point clouds. In this case here, we have a 5-to-1 internal resonance, that then devolves into just a stable periodic orbit. I believe we also did this for the second loading scenario where we excited the NO. Here's the receptance plots. Keep going. Here is our, we end up breaking this into different regimes, and you can see before and after the disturbance and loading scenarios for this behavior. We sampled a couple different points to see what was going on here. We'll just give these a second to load. Here you can see we've got two fixed, one fixed point, meaning periodic for both before and after disturbance. Same thing here. Actually, the same thing here, same thing here. Here you get these quasi-periodic responses. You can also see in the Fourier domain. Come down here. Here, it's tough to say. This is either an aperiodic response or some extreme. I mean, given this looks periodic, it's maybe some very high internal resonance, maybe like a 15 or a 19 to 1. It's hard to tell at that point. Same thing here. Here you get quasi-periodic that turns into nice periodic response. This is just a point cloud, and it's aperiodic. Same aperiodic here, quasi-periodic. And that is the end of this, where we did these measurements and computed these point coordinates. So you can also do this for a multi-degree frame system with forcing. However, you end up having to plot both of the displacements at the same time. But you could extend this to many degrees of freedom if you wanted as well. You just get more and more complicated plots.